So basically, the null hypothesis is so let me put it this way. If I have if I make a claim that the average the cumulative grade point average of unilag student is 3.5 without making any research, I just assume that okay, this will be the truth. Then I'll come up with an alternative hypothesis that this can be that okay, I think the it's actually greater or lesser. So in case of a null hypothesis, you assume equality for a particular group, then the alternative hypothesis uh, takes the opposite. So you now want to reach a conclusion that okay, whether to accept the truth, the claim which is my null hypothesis, or you fail to accept it. So you say you can sometimes they say whether you reject or you fail to reject. So that brings us to what we call the level of significance or the p value. Either of the case, whether talking about this level of significance or the p value. We're going to see how this applies as we go in the session. So, so hypothesis testing is conducted in the following manner. First of all, state the hypothesis. You're going to have your null hypothesis and the alternative hypothesis. Then the next thing is to formulate an analysis plan. Then in this case, you're going to talk about your test statistics. What is the kind of uh, test statistics you want to use for this particular hypothesis testing for this particular analysis. Then you analyze sample data. This stage involves the calculation and interpretation of test statistics, in this case, as described in the analysis plan. So that's in the second stage. Then you're going to interpret the results finally. This stage involves the application of decision rule described in the analysis plan. So you need, what you are saying in this first step is that okay, after you in the second step, after you say test statistics and all of that, then you do some calculation and all of that. Then with this calculation, the result you now get is now what you use to make a decision whether you're gonna reject the null hypothesis or you fail to reject the null hypothesis. Now let's move to the next slide. Now this takes us to what we call decision errors. We have the type 1 error and we have the type 2 error. So what's type 1 error? So type 1 error occurs when the researcher rejects a null hypothesis when it is true. Type 1 error occurs when the researcher rejects a null hypothesis when it is true. And what's type 2 error? Type 2 error occurs when the researcher fails to reject a null hypothesis that is false. So let me give you a layman illustration. For example, someone was charged with for a particular offense. Now, suppose that person is actually guilty. No, let's say the person is innocent actually. So let's say the person is innocent and the judge, not knowing, sentence that person to maybe 10 years imprisonment or sentence the person to death or any case it may be. In that case, that you say that judge just committed a type 1 error because that judge actually rejected a true null hypothesis. So the charged person that was charged that was actually innocent is the true null hypothesis in that case. You understand? And the type 2 error is the other way around, whereby okay, someone that was charged to court, but he was actually guilty, but the judge actually sets the guy free that he should do that he should not actually guilty of that offense. Then in that case, you say that judge committed a type 2 error. I hope that actually makes a lot of sense to us. Does it? Hello, is there anybody there?
I can hear you.
Okay. Moving forward, I hope we got the illustration I just gave to guide the two types of error we have. Hello, hello, can you hear me? So I asked that, did you get the illustration I gave about the two types of error we have? Okay, no problem. So moving forward, so using the student t-test. Now, the student t-test is a method for comparing two samples. It can be implemented to determine whether the samples are different. In this case, this is a parametric test, and the data should be normally distributed. So how can handle the various versions of t-test using the t.test command. In this case, we have two types where the one where the two samples have equal variance and any two samples does not have equal variance. So as soon as the two samples does not have equal variance. So the test can be used to deal with two and one sample tests as well as paired tests. So this is the command. Generally, you can do on one sample, you can do on two samples, depending on what you want to do. So the basic method is the t.test, which the t.test, that's the command, that's the function you use. And there are some parameters that you can include. That's var.equal. By default, it's false. But it might set true. You are saying that the two samples has equal variance. Moving to the next slide. Here, yes. By default, you say okay, the mean is zero. The mean is set to zero by default. So you can set that parameter that definitely. So if this one sample test is carried out, MU indicates the mean against the sample should be tested. Then you have the alternative parameter which sets whether you want to make do a directional hypothesis or a non-directional hypothesis. So what's the difference between these two? So this is what I'm talking about. Let me go to here, whiteboard marker. So I'm waiting for this guy to load now. Okay. So yeah, as I was saying, I said you can have a non-directional, say ND. ND means non-directional, then you can have directional. So non-directional is when you have this case. Then directional is when you have this case. So non-directional hypothesis is saying that I said your null hypothesis H naught assumes equality. Is going to say maybe the mean of the first sample is equal to the mean of the second sample. Then your alternative hypothesis can be this scenario or this scenario or this scenario. So when is this particular scenario, when you are saying not equals to, it's non-directional because it can either go to the right or to the left. What do I mean? That it can actually be greater than or less than. So you doesn't have a direction. You say it's called a non-directional hypothesis. But when you say greater or less, it has a direction. It's greater, which is to the right, or it's less than, which is to the left. So I can say my H. So if my null hypothesis is, I can say my H1 is that the mean of the first sample is not equals to the mean of the second sample. So in this case, I'm performing non-directional hypothesis test. So I believe that is clear. Let me go to here. I have it. So when you're using the formula syntax, you can use this command. Conf dot level is you are setting the level of or confidence level, or you can say level of significance, any which way you want to put it. That if you want to show the confidence level of uh, the analysis. So, for example, you can say the probability of me coming to office is between 0.7 and 0.9 or 1. So that's you are giving yourself a confidence interval, right? But so you use the level of significance. You can set confidence intervals with it. But this one is talking about level of significance. How far we're going to talk about level of significance later in the session. And see that this second is the last part of I can see my cursor on is when you're using a formula syntax to perform your analysis. Then you can use this subset function if you are performing your uh, maybe your t-test based on some categories in your data. Say for example, you have a data like this. Let me erase this part. So you have score, and you have grade. So I have something like 70, 80, 50, 60, then 20, 10. Then I graded this one to be say good, good, average, average, bad, bad. I can say poor any which one. So you can see that this data set have three categories. 1, 2, and 3. So if I want to do my t-test, I can only do for two categories at a time. So but if I'm performing a t-test on this kind of data, I have to select the two categories I'm picking. So whether it's the good and the average, whether it's good and the bad, that's why you have to use this subset parameter that I have here right on my screen. So as you can see here, subset is equals to predictor in say sample one, sample two, depending on the categories. We're going to see this later in the slide. Okay. So performing the two sample t-tests with unequal variance. So we know that they use the t-test command. Okay. So you have a data 2 and a data 3. The test into data 2, data 3. So you have two samples called data 2 and data 3. Here you can see that you have Welch two sample t-tests. As a result, this already was okay. You are performing on data 2 and data 3. These are calculated value. This is our degree of freedom. So if you are performing a Welch uh, t-test, you usually have a fractional degree of freedom, as you can see here. But normally, if you are performing a normal student t-test, you won't have this kind of degree of freedom. So our p-value is set with this. So it is this p-value you use to come to a conclusion, to decide whether you're going to reject the null hypothesis or you fail to reject the null hypothesis. Now, how do you decide? In this parameter, we have by default confidence level to be 0.95, which is like your alpha. So it means your alpha in this case is 0.05. That's the 1 minus 0.95, what you have here. So your alpha is 0.05. So it's your alpha and your p-value you use to come to a conclusion. So let me go back to my so t dot test data 2 comma data 3. These are the two samples I'm testing. Right. So your null hypothesis is like the mean of the first sample is actually the same as the mean of the second sample. So your by default, since you are not putting the alternative parameter, by default it does a non-directional hypothesis. That is, your null hypothesis in that case, sorry, your alternative hypothesis in that case will be mu1 not equals to mu2. That will be your alternative hypothesis. So this is what I'm saying. In that example I gave, yeah, you are going to have a null hypothesis of this is going to be your H naught that mu1 is equals to mu2, and that's going to be your null hypothesis. Uh, mu1 not equals to mu2 because it just specified the alternative parameter. So now your alpha is 0.05, which is actually 1 minus 0.95, which is a confidence level. Now your p value, whenever p value, your p is greater than 0.05, what do you do? Say you fail to reject decision. So let me write decision. Fail to reject H naught. You fail to reject H naught. But but when your p value is less than 0.05, what's the decision you're going to take? The decision is that I'm going to reject I'm going to reject H naught, which is my null hypothesis. So okay, moving to our slide again. So in this case, my p value is this, which is 0.009, which is actually less than my alpha. So in this case, what do we do? What do we say? We say we reject the null hypothesis, and we're going to say the mean of the first sample is actually not the same thing as mean of the second sample. So what does that mean? Literally, it means that the mean of this guy is significantly different from the mean of this guy. So it's like they are not from the same population. So
It's two of us alone that are in the class. Is there any other person in the class?
not for now.
But you are recording the session.
Yes, sir.
Okay.
Okay. So you can see here true difference, alternative hypothesis, true difference in means is not equal to zero. True difference in means is not equal to zero. What this one actually means is that from this place, it means from this guy like this, it means that mu1 minus mu2 is not equal to zero. By the time I take mu2 to the other side. So that's why this one is saying that true difference in means is not equal to zero. So that's what the alternative hypothesis is saying. All right. So you have the one sample to test. So for any analysis, each pools of data are collected and tested using random samples taken from the population. So researchers have to test samples to determine whether which population they were taken from. So say whether this particular sample is a true representative of a particular population. So we can say carry out the one sample to test in that regard. So don't forget that our mean by default is zero, but you have to set your mean if you are doing a one sample test. So in this case, yeah, by default, if you don't set the mean. So in this case, I'm saying I'm doing a sample test from data 2, and my mean is 5. So it's going to compare based on this mean and say, I didn't specify the alternative hypothesis, the alternative parameter. So this one, I'm saying that my null hypothesis that mu1, that's the mean for this data 2, is actually equal to 5. So my null hypothesis, my alternative hypothesis now being my mu is not equal to 5. Are you with me? So, this is a one sample test, and you have your calculated value, you have your degree of freedom, your p value is this, and in this case, you can see that my p value is greater than my alpha. So it means that I'm going to fail to reject the null hypothesis. You understand? I'll fail to relate the null hypothesis. That's the decision. Whenever the p value is greater than 0.05, which is the alpha, you fail to reject the null hypothesis. That is the H naught. So alternative hypothesis, true mean is not equal to 5, at least mu minus uh, mu is not equal to 5. Yeah. Okay. Sometimes in practice, in maybe when you are you are in school, you did statistics, you might actually find for p value it's they use the calculated value for c. No, they find the table value rather. So this is the calculated value. They're going to find the table value. So they are using a table value for this instance to make a decision. You don't use your alpha. You're using a table value. So you're going to compare your table value with this particular calculated t value. Now, whenever your calculated value is less than your, let me go into that. Let me just proceed. So using directional hypothesis. So in this case, you can see that there is specified alternatives to be greater. So that's a directional hypothesis. So it is greater or it is lesser. That's a directional hypothesis. In this case, my alternative is greater, and they perform the test statistics and all of that. I have a p-value greater than 0. You can see that here my degree of freedom is 15. So how do you get 15 here? Which is your degree of freedom? Since it's a one sample to test, it's going to be the length of or the sample size of your data minus 1. That's going to be your degree of freedom. So it means that the data here, the length is 16. So in practice, let me even do let me perform a test in practice using my app. Okay, let me go to the new sheet and type it. This. Okay, go to the new sheet. So let me go to the sample. 2, 3, 4, 3, 2, 4, 5, 1, 6, 7, 9. What's the length of my data here? Length of data 1 is 16. Okay, so t dot text of data 1. Let's specify my mean to be 86. So if you can see here, one sample test data is data 1. This is my value of see my degree of freedom is 15. That's 16. The length of data, which is 16 minus 1, and my p value is this guy. So you can see that here my p value is 0.000, which is actually less than 0.05. In that case, I'm going to reject uh, the null hypothesis. So if I'm rejecting the null hypothesis, it means I'm accepting this particular alternative hypothesis that true mean is not equal to 8. So if you actually check it, it's going to find the mean of your data exactly. So this is the mean of your data, which is 4.8, and 4.8 is actually different from 8. So it means your guy, you are going to reject that null hypothesis and say that the true mean is not equal to 8. All right. So moving forward. Oh, okay. Is using the formula syntax. I'm doing a test on rich and Greece column for the data called grass. I can subset if I have different categories. This is going to perform a test on these two columns. And here I'm subsetting because this particular quiz has more than 2 categories. So let me show you that instance here. So let me show you what I'm talking about. So I'll say score. Score is I get the score to 80 70, 50, 55, 60, then 20, then 5. Then I would say grade is equals to good, bad, poor. I'm going to repeat this one times, and 3 times. So repeat 3 times. Not appendix. Not appendix physical. I want to form a data frame. Repeat this times. So I'm going to create a data frame with these two vectors. The data dot frame of cbind score comma grade. Let me call df for it to see. This is my data frame. Now I want to do a t dot test on t dot test on score. So I want to immediately against degrees, yeah, degrees data is equal to df. Remember that that's more than 3 categories, so this should throw up an error if I should write this. So I can see error in this object grid not. Sorry, it's not. It's good down to write. Good. The grouping factor must have exactly 2 levels. So because I have more than 2 levels here, that's why I'm having this error. So I have to subset and tell you, okay, I want it for just particular uh for a particular group. So that's why I'm going to put this parameter called subset. So I'm going to rewrite this guy and say subset equals to grade in, to in what say good and poor, for example. Then I want to be uh did I miss anything? Okay, I did put a comma, sorry. What's missing validate subset. I already specified it variables. Uh, why are we having this? Good and poor. So let me do good and I wanted to have something not let me say average, not bad actually. Average. And reduce then poor. Set fragment is not numeric or logical. Uh, I don't know why I'm having this difficulty. So it's supposed to this how it's supposed to perform the test for me. So it's going to do it for 2 categories. Say the good. So for this good, it's going to perform 2 categories. So we're going to compare the mean of this guy of this category and the mean of this category and say is there a difference between these 2 categories? So I'm going to give you a t test and a p value, a t value and a p value in that case. So obviously there's difference between obviously there's difference between these two categories. You can see that the good the scores that are good they are higher compared to the scores that are poor. So it's going to tell you whether there is a significant difference between these two categories. That's what you're supposed to have. But I don't really know why I'm having difficulty with this particular command here. Yeah. So yeah, that's that for that. All right. So let's carry out a student test on some data. As soon as you have a file contain data containing blah 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 blah, you know how to perform the test into close comma open. Then you specify the data which is what shop because the data is actually shop. So moving to the next slide. So talking about the unit test, which is a non-parametric test, just as the t-test also, you provide maybe one or two samples. If you want to perform a one sample test or two sample test, you have the mean parameter set to zero by default, the alternative parameter. Then, if you need the confidence interval, you can set it to true. Then, you have confidence the level the correct equals to true. So, this is the continuous correction. It's set to true by default. Uh, Paired is equals to false, set to true. Now, I didn't talk about the peer test in the student test. I don't know why we didn't talk about that. So the peer samples, the peer test is like, okay, suppose two samples, for example, let's say we collected data about some set of people that, okay, there are some set of people they want to work out. So before, okay, there is a particular trainer that was training them before on working out and stuff like that. So you collected data about their weight. So so they now change to another trainer. So the first trainer you collected the weight of this set of people. Then when they were now assigned to another trainer, so after that trainer trained them for a particular period, you now collected another sample of their weight of this set of just same set of people. Now you want to now perform a t-test, you know that okay, is there a significant difference between the performance or the weight of these people when trainer A was training them and when the new trainer B started training them? So in that case, that kind of test is called a peer test because two of them are kind of related. So you say you are doing a peer test. So you can set fear to be true if you are in that kind of it is that kind of analysis you are trying to perform. All right. Okay. So you use the test function to perform the view test. So you have reconcile rank test, function test with continuous correction. You have data one, data two. This is your calculated value, your p value. Your alternative implicit true location shift is not equal to zero. So the same way you use your p value to make decision in your t test, that's the same way you use it to make decision in the u test. Also, is performing the one sample test. So reconcile test with multiple position. You have data one. Uh, in this case, instead of having the W value, you have use a calculated value here. You have a P value, then you make your decision based on your P value. Here you are given that true location is not equal to zero because you didn't set parameter for mean. So by default it takes value zero. Okay. Okay, yeah, as I already seen here that if a single numerical vector is specified, a one sample test carried out, the default is to set MB to 0. Okay, you can also use the formula syntax and subset based on categories you want to make your analysis on. Okay, so let's carry out unit test on some data. Assume that we have a file this which consists of butterfly data called BFC. This comprises two columns, namely grass and health, as shown below. To carry out a two sample unit test on the two samples BFC data object. So carry out a one sample test on the grass sample of the BFC data, set the hypothesis that the location shift is less than 7.5. In this case, you have to perform the two sample test on the two samples. So you say p wacons dot test into brackets grass column comma health column comma data is equals to BFC. So that's going to perform two sample tests. But in this case, the second case where you are saying that you want to perform a one sample test on the grass sample of the BFC data, the grass sample is the first column. Set a hypothesis that the location shift is less than 7.5. So what do? You're going to say b becomes dot test into brackets grass data is equals to, or you say BFC appercent grass comma MB is equals to 7.5. Then you set your alternative to be uh, less 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 or less than you use. So for example, let's do with this guy. Suppose I want to do it with the score column here. Not score, let me see if data one. Real cost get data one. Then I will say MU is equals to 7.5 alternative is equals to less or lesser. Less rather less. So you have this how you perform it. So, alternative two location is less than 7.5. As you can see, two location shift is less than 7.5. That's how you perform the test. All right. We talked about peer. So this was talking about PLC and unit test now. So consider a situation where the field data is available. A data set containing information of marks of students before and after training, or weight of peaks before and after 1 month. Because they are kind of related, you want to do a kind of comparison about this information, then you can use a peer sample, a peer test. So in that case, the additional parameter is set to set peer to be equals to true. So in that case, your null hypothesis is going to be so first of all, let me go to the next step. So in this case, you are trying to do a purity test on count and trap. They didn't show us this guy. So let me use my command on R here. Here I want to between these two guys. Okay, I didn't create another data too, so let me create another data too, for example. Data two is oh, so let me create another data two, say 2 comma 3 comma 5 comma 7 comma 4 comma 6 comma 7 comma 8 and that will be the same thing because that will be the same length comma 10 comma 7. This is up to 16 years, I don't think so. Comma 6 1 6 now comma 6 points 1 2 3 4 5 6 7 8 9 10 11 12 13 14 2 comma 4 1,6. Yeah. So then perform the get test. So t dot test of data 1, data 2, get equals to true. So I have here paired t test. Determine that you see that t value, the degree of freedom is 15. P value is this guy, 0.02. The time hypothesis true difference in means is not equal to 0. So here, what does it mean? The p value is less than 0.05. In that case, you are going to what? What's going to be your decision?
These are not true.
What's the decision? What's going to be the decision?
Not true because this one
It's not true. No, what's the proper way to say?
the
So you are rejecting the null hypothesis. So it means you are rejecting the null hypothesis. So if you are rejecting the null hypothesis, it means I'm accepting this fact that there is a significant difference between the mean of the first sample and the mean of the second sample. So there's a significant difference between the mean of this guy and the mean of this guy. So basically, you can see that the degree of freedom is 15. Where is it? Okay, because yeah, it's 15 because you are doing uh, a peer test because you are comparing two of them, so it's going to be the sample size of just one of them minus one. So, so let me do something for you now. Let me show you something. If I should, both of them are of the same length. Now let me make the length of the first, the second one to be smaller, say 15. Now let me do the peer test for you now to show you. You can see there's an error. Say error in computer cases of x comma y. Not all arguments have the same length. It does not have the same length. So you cannot do a peer test if it does not have the same length. But let me say I don't want to do the peer test now. Let me run this command down. You can see that I have something now. To give you the mean of the first guy and the second guy, this is the mean of the first sample, this is the mean of the second sample, this is my conclusion. My p value is this guy, which is greater than 0.05. So you can say that at 0. At 95% level of significance, I'm sure that there, there is no significant difference between the mean of the first sample and the second sample. I have a word, I have a word to sample test here uh, because by default your variance dot equal, you are saying that they are not of equal variance. But if I set that parameter to be true, then I'm going to have a standard two sample test. Let me say var dot equal equals to true. So you can see here I have a two sample test instead of a word two sample test. So I have a standard two sample test, and my degree of freedom is not fractional. So my degree of freedom is 39. So why is my degree of freedom 39? My degree of freedom is 39. How do you calculate the degree of freedom? It's going to be the length of this guy, and the sample size of this guy, plus the sample size of this guy minus 2. That will be 16 plus 15, which is 31, minus 2, which is 29. So I hope you understand that part. Let's proceed.
because you added by
So moving forward, uh, So let's conduct peer t-tests t-tests on sample data, assume that we have a file to this. So this is the sample data. We are told that carry out the peer U test on this data, carry out the peer t test on this data, set the time hypothesis that the difference in mean is 1, and show the 99% confidence interval. They say show the 99% confidence interval. So how do you do this? So I'll do that with that example again. I'll set mean to be 1. So let me do uh, so let me go to my app. So I'll do this to make the sample size of this one be 16 again. That can perform the sample test or the peer test rather. Okay, so go back to this. I'll put this peer to be true. Okay, mean to be 1. I think that's what they told us to do. Yeah, it says difference in mean is 1. Okay, and show the 99% confidence interval. So if you don't forget, let's go back to where it shows that here set conf.int is equal to false. Sets whether the confidence interval should be reported. Set it to be true if you want it to be reported. So okay, okay, sorry. So go back to our app. Uh, here's my app. So let's see if I can do this with this conf.int or conf.int. Uh, I don't think the t test has conf. So let me just. So I'll put conf.level to be 0.99. So this is going to set the level. So as you can see here, these are t tests as so I'm testing at 99% level of significance. So this is your p value. So at 99% level of significance, I will be rejecting the null hypothesis and I'll be accepting this part that the true difference in mean is not equal to 1, and this is the confidence interval. As you can see, 99% confidence interval. The same way you do for the U test. All right, moving forward. Okay, let's talking about correlation and covariance. We so when you have two continuous variables, you can look for a link between them. So this link is called a correlation. So how are these two guys, two variables, how are they related? Are they positively correlated, negatively correlated, or they don't have any correlation at all? So the correlation command determines correlation between two vectors. So all the columns of the data frame, all two data frames. Why the COB command examines covariance. So we can also perform correlation test. Where we are going to use the codex test to test for the significance of the correlation. So in this case, talking about correlation, So if I have two variables x and y. So let's say I have this guy. So this is my y, this is my x. So if I have something like this, a line like this, I will say that this guy, x and y are positively correlated. sorry, don't let me write this. Just let me write it because that possible regret. It means increase in X causes what? Increase in Y. Increase in X means increase in Y. For example, increase in rainfall because increase in sales of umbrella. Think about it. So moving forward, uh, if I have something like this, then I'll say I have a negative correlation. This means increase in X causes what? Decrease in what? In Y. Increase in X causes decrease in Y. Now, when you have no correlation, then you're talking about something like this. You have just whether it is parallel to the X axis or it is parallel to the Y axis, then there's no correlation. It's, yeah, so it's parallel to the X, parallel to Y, there's no correlation at all. So correlation value lies between -1, 1. A value close to 1 is said to be shows a positive correlation, a strong positive correlation. And a value close to -1 shows a strong negative correlation. A value that is 0 or close to 0 shows no correlation. Moving forward. Alright. Okay. So here, performing simple correlation. This you are performing a correlation between the count and speed codon. Let's just perform that simple correlation with. So we have two type of correlation. You have the Spearman correlation. You have the Pearson product movement correlation. Spearman rank of Pearson product movement. So by default, I think it's just the Pearson product movement. Yeah. So let me see the next step before we go to this command for covariance. So let me go back to let me go to our let's just perform a simple correlation between data 1 and data 2. Or let me use the iris data set. So data set iris and I say correlation between iris ampersand sepal length and iris ampersand sepal width. We will iris ampersand sepal width. Here I have minus 0.11 baked to 0. There's really no correlation. So that's correlation for you. The CF command is used to perform the covariance, check covariance. So we have the Cohort2 core. This command is used to determine the correlation from a matrix of covariance. So it's used to check the correlation of a matrix of covariance. So you perform a correlation in a matrix of covariance. If you perform a correlation in a matrix of covariance, then you perform what we call Cohort2 core. So before you can use this command Cohort2 core, it means that you already have a matrix of correlation. So a matrix of covariance. So if I have this first command, which is COV women, I've saved it in a particular variable, then I can perform Cohort2 core on that particular variable. So because this command I've already generated a matrix of covariance for me, and I'll just use this guy uh, to perform correlation on that matrix of covariance. So for example, I want to say covariance of say iris 1 for empty. This is a matrix of covariance, for example. Now. So I'll now say, okay, I can say iris, I'll assign this to iris underscore c. So I'll now perform code 2 call on this covariance of matrix, for matrix of covariance. And I have this result. So this is the correlation between this matrix. So this one just perform okay, correlation between this and correlation in variable and itself gives you a perfect correlation, which is one, gives a perfect number. So you can say all this one that has one, one, one are just correlation with themselves, a perfect one. So this one shows a strong positive correlation. This is an example of a strong positive correlation. Also uh, this and this strong positive correlation. All right. So let's move to the last slide. So statistical testing in correlation test. So here you are doing a correlation test on these two variables. So I said by default, if you are not setting any, the kind of uh, correlation you want to perform, whether Pearson or product, Pearson product movement or SPMR, it does the Pearson product movement correlation for you by default. So this is what you have. You also decide based on your p-value. So if your p-value is greater than 0.05, so you see that it's greater than 0.05, so you are going to fail to reject the null hypothesis. It means you are going to accept the null hypothesis and you're going to say that there is a true correlation between the two variables. So, but if you are rejecting the null hypothesis, then you're going to accept the alternative hypothesis and say the true correlation is not equal to zero. It means that uh, there is no uh, oh, I think I made a mistake. The null hypothesis is actually that the how should I put this? There is no correlation. Yeah, there is no correlation between the two variables. So that's null hypothesis. There is no correlation between two variables. Now, so if you are rejecting the null hypothesis, since you are accepting the alternative hypothesis that there is actually a correlation, so you can say that the true correlation is not equal to zero. All right, moving on. We can also use the formula syntax. Also use the formula syntax to perform the correlation test. Here I'm using the SPMR correlation. All right. So moving forward. So before I move on, let me clarify how the null hypothesis looks like for the correlation testing. So for the correlation test, so this is the null hypothesis. So the null hypothesis is something like this. So let's say alpha is our correlation value. So your null hypothesis is that alpha is equal to zero. Your alternative hypothesis can be either of these three. It can be this, it can be this, and it can be this. Either of the case. But your null hypothesis is saying that alpha is equal to zero, which means that there is no correlation. If I say alpha is equal to zero, if your correlation value is zero, it means there is no correlation. So that's what your null hypothesis is saying. So if you are rejecting this alpha, this H naught, it means you are accepting this guy, which actually means that there's a correlation. So there's correlation. It means explanation between those two variables you are trying to compare. Moving forward. So don't forget I told you that your H note assumes equality, so don't forget that part. You are going to be asked this, you should understand this concept because you are going to be tested in it in your certification exam. All right. Now, test for association. The chi-square test. Now, chi-square test is very important. You are not going to be tested on this in your certification exams. So, your chi-square test is used to, it's called test for independence. We call it chi-square test of independence. They will say test for association. So, majorly, if I have two columns, say for example, how do I think in the next slide I will have a better picture of how to explain this. So basically, these are the parameters takes x and sometimes your y is optional. So it performs a test on a particular, it uses the consistency table between two columns if you have two columns that you're trying to compare in this case. So let's look at the next slide so that we can actually see what you. Okay, oh, they didn't show this. They didn't show this. Why didn't they practice this? But then I think we are going to see in it. So goodness of fit test also. So why fitting a statistical model for observed data, analysts must identify how accurately model analysis is. This is done with the help of the chi-square test. So a chi-square test is a statistical test that provides goodness of fit. That tells whether the observed data is taken from the claim distribution or not. Let's see the next slide. Now this is a perfect illustration. Now this guy is a contingency table created between I think habitat and species. I think you have species. These has different types of species and different types of habitat. So you have this particular species uh, in this habitat. You have like 10 of them in this habitat. You have like 8 of them in this habitat and stuff like that. So what you're trying to test is that uh, you're trying to test that is species dependent on habitat and two of them are dependent on each other. If not, then you say species and habitat are independent. So it's used to test for independence. So let's see the next slide. Oh, they didn't show that. They didn't show that. So basically, it's used to test for independence. So carry out the basic chi-square test on this data and save the result as a named object. It's really basic with the students. I'm going to explain some basic concepts, but you have to read up on it because I won't talk about everything. So there's not enough time to talk about everything. But let me show over the summary. Okay, so let us show us performing the chi-square test. So let me show you an illustration. So which data can I use? Okay, let me just go back to my no. I don't have wow, wow. I don't have this. Oh goodness. Really spend. I'm looking for a particular data set that I can use. Custom operation vehicle. No, Sorry, let me check this. Daphnia employees. Um, hepatitis. Uh, I can't. Wow, I can't see perfect data. Please let me check the inbuilt data set in R that I can find one. Wait, so um, I can't really find. I can't. So okay, so you're gonna have a set of contingency table to perform this illustration. So let me use. I can't use. I can't use this. I can't use this. I can't use this. I can't use this. Okay, let me just use this table of. So let me call this on top. I take chi dot chi square dot this. So this is not exactly what I wanted to be. I will have a 2 by 2 contingency table to compare this guy. So it's not perfect. It's not a perfect model. So if you have a contingency table of this format that I showed earlier, yeah, then you're able to see depending on the p-value whether there is there's a relationship between species and habitats. In that case, say they are dependent. So the null value, the null hypothesis is going to be there is no, or the two columns are independent. So let's say species are independent, species and habitats are independent of each other. There is no relationship between them. And your null hypothesis, your alternative hypothesis that there is a relationship between species and habitat. So depending on the p-value, you're going to accept of if you're going to reject or fail to reject the null hypothesis. So that's the scope of the hypothesis testing app. So you can go to your folders like your post snippets, in your uh, the lab you downloaded on your PC. You see some post snippets there. You go to hypothesis testing and practice the lab session. Go to the lab manual. You're going to understand better. All right, that's it for hypothesis testing now. So let's go to task analysis on massive scale. Talking about how I do map out. We're going to wrap up the session with this. So here we're going to understand key requirements for data analysis on massive scale, install and use R to perform text mining, understand my out features. Uh, this uh, to this you might have to complete some of this uh, lab on your own because there will be no time to actually do this because we are actually lagging behind. But let's see how far we can go. So the amount of data that is traditionally processed by typical static analysis tools and systems earlier used to be in the range of say 10 and hundreds of gigabytes, definitely not a terabyte or petabytes in this. As in the case of big data, often traditional analysis required an expensive SMP machine with huge memory to hold data being analyzed. So, for example, take Alpha instance. R runs in memory. So R runs based on memory available on your local machine. So it can run on data sets that's more than the memory of a machine. So, so in that case, you are limited to the amount of data you can analyze using traditional methods. So the reason behind this is that many analytical algorithms were quite compute intensive and were designed to run in memory as they require multiple and often frequent passes through the data. So, so sampling technique as a solution was implemented, like what we just did in hypothesis testing. So the idea about hypothesis testing is actually having to generalize, having to find a sample out of the data you have. So you can have petabytes of data, terabytes of data, and you need to make sense out of the data. But you can't analyze all of the data set. But you can find a sample out of a population that is a true representative of the population, then you can use that to come to a conclusion, a good business decision, having to analyze that sample. But finding that statistically significant sample is actually a challenging and very sparse, very challenging thing to do. So it's very challenging for sparse and obscure data sets, which are quite common. So the scale on which analysis requires to be done is dependent on various factors and complications. So, but these factors and complications include the volume of data on which analysis is done, the number of transformations required on that data set before applying statistical models, the number of pairwise correlation needed to calculate, the degree of complexity of the statistical computation, the number of statistical models they applied to the data set. So we have a lot of factors to consider. So now I do as a solution because I do provide the solution to the problem of performing analysis on massive data scale by providing a platform to perform massively parallel processing computations on data. Because you can actually do your analysis on the whole of the data set instead of considering just a sample. So why map is a solution for parallel processing of data set in Hadoop? Converting statistical models to run in parallel using MapReduce is not easy because you have to write Java. This MapReduce is written in Java. So not as many analysts or statisticians will be able to handle MapReduce programming efficiently. As a result, Hadoop developers keep working on solutions for implementing their algorithms required to perform statistical modeling and analysis without overburdening the analyst the knowledge of parallel programming. Because MapReduce is written in Java and not many analysts or statisticians can be able to handle that. So two sources integration of R language is Hadoop, which we call R Hadoop, and also map out its multiple statistical models and library functions. So let's do a recap on Hadoop. So Hadoop is an open source software application that provides distributed storage, which is HDFS, and computation capabilities for processing large amounts of data, which is the MapReduce part of Hadoop. It's based on a distributed file system and allows users to perform parallel executions of program on a group of computers, also known as the Hadoop clusters. So Hadoop distributed file system HDFS is the storage components of Hadoop, and the components is optimized to work with large amounts of data, like very large amounts of data. So this layer contains following two subcomponents. You have the name node and the data node. So the name node is the one that keeps the metadata. So it keeps record of data nodes and pipelines to manage the data nodes. It's all the information about the data, where it's stored, when it is created, and all of that. So the data node contains the blocks of files and communicates with other data nodes to manage file read and write function.
the data not contain they say contains blocks of files. So what this means is that if I have a file of 200 gigabytes, so this file is going to be broken down into blocks, usually of usually 128 MB. So you have that side that 200 gigabytes being broken down to different blocks set in different data. You can read more on that on the first module of this course. I think they explain better on what data is that regard. So talking about marketplace, which provides a cloud-based distributed computing environment for the hello?
Are you still there?
Yes, I'm with you. Can you see my screen? Hello? Can you see my screen? Okay. So this component performs parallel processing of large amounts of data, such as social network data, relational data from database, and also data generated from user interactions on the internet. So, so micro:this processes a job by dividing it into small parallel map functions and reduce functions, which is called the map and the reduce part of it. So it's the combination of map and reduce. So the mapper, so you have the mapper part and the reducer part of the function. The mapper part is the one that works on the splitted, so split takes in an input. So you have the data, it's split into equal sizes, and the mapper works on it. And after the mapper has worked on those uh, splitted inputs, it's, it collects it in form of a key value pair and also sends the results. The output sent from the mapper is sent as an input to the reducer. That process of sending output from the mapper as an input to the reducer is called a shock process. You should take note of that. So, so integrating R and Hadoop, which is called or we related as well called R Hadoop, it's an approach of integrating R and Hadoop. This enables us to use the capabilities of R in the Hadoop environment. So it's an open source project that allows programmers to define their own map and reduce function and directly use the functionality of map in our code. This project was started, process developed by Revo, Revolution Analytics. Yeah, I think that's the name, Revolution Analytics. So our developers programmers to make use of full features and existing environment of R and leverage the Hadoop platform, especially the age-based ATFS and the map pages. So how are they going to following the key packages? The RHDFS, which enables us to use the ATFS environment, the RHBase, which enables us to access the age-based table, the RMR2, which allows you to write your own map with this program. So in here, so to install RHDFS, you first need to install all these packages: RJava, RCC, RCPP, RJCU, and the shape 2. So after you install this, then all the process you have is on your manual. You can do through it, but you have to have your VMware where to do that. So you are using R to process a large amount of data stored in tables. To manipulate this data, which are the following R packages you use? You only use the R base in that scenario. So describe the distribution of how the content of this one. All of this you're going to have it in your book. Now talking about text mining for driving useful information. So text mining is a set of techniques and methods for automatically processing natural language text available in large quantities. This text can be in the form of the files. So, the aim of text mining is to extract and structure the text for quick analysis or non-literary analysis in order to discover hidden data or automatic decision making. So, but it's different from stylometry, but has much in common with lexicometry. So it's an extension of lexicometry using advanced method of multidimensional statistics. So basically, text mining is equal to lexicometry plus data mining. So because data, you are trying to get text in large quantities. That's what data mining and lexicometry trying to judge the structure. So that's why you say text mining is lexicometry plus data mining. So moving to the next uh, slide. So this gives us this process, the text mining process. So first of all, structuring the input text, adding some language rules, probably moving useless terms, depending on language rules. So also inserting the structured data into the database after you be able to structure your input text. You added some language rules to remove useless terms. And all those after this process have been done, you have the particular output, then you start to the database. Then you can furthermore identify patterns in the data that you've stored and analyze the patterns and generate useful insights from it. Okay, so here talking about implementing text mining in R Hadoop. So one of the common application of R Hadoop is text mining. So we have the TM package in R which is used for that instance. Okay. Sorry. So they say this package contains about 250 news articles with additional metadata information in the form of this guy. So this package is developed to work with plain text, articles, papers, surveys, and web documents in form of the hypertext markup language and the extensive markup language and standard generalized markup language. I think further information is inside your material. This is also essential. You can be asked some questions under this. Talking about my out, it's an open source project from Apache offering Java libraries for distributed or otherwise scalable machine learning algorithm. So these algorithms include key machine learning techniques such as classification, clustering, association, goal analysis, and recommendations. So when you talk about map out, so what you come up to your head is machine learning algorithms. So it's not for this. So map out can run independently, but it's also implement map with paradigm. So it works within Hadoop and can perform machine learning over large datasets on Hadoop cluster. Okay. So there are three main categories of map out algorithms for supporting statistical analysis. These are collaborative filtering, clustering, and classification. You should take note of that. I think this should show us, yeah, the map development over the other framework. So we have these three categories of math algorithms: collaborative, filtering, clustering, classification. You can also have user-defined algorithms that you can create by yourself to perform the specific task. So it uses the MapReduce API. Also use MapReduce processing framework. You can also use Yarn as a source manager, and it also depends on the Hadoop. Can also depend on the Hadoop distributed storage system. All right. So talking about collaborative fixing, so Marathon was specifically to serve as a recommendation engine. It is used it used a collaborative filtering algorithms. So what do we understand by collaborative filtering? Uh, it's just more of like, okay, let me use this illustration. Say in a supermarket, the customer, one particular customer made some choices or made some choices about some particular goods in your store, and another customer came a particular day and was making such, so was going in that pattern of that customer that came the other day, and so uh, based on that selection, you recommended that okay, if you chose this particular goods, you might want to get this also. So that maybe that particular customer when he came, he bought bread, and next thing he bought egg, and next thing he bought sardine, and next thing he bought some stuff. And another customer now came, the person bought bread, the person bought egg. You might have to suggest that maybe you like to buy sardine and stuff like that. So the recommendations can be applied against user preference, taking into consideration the behavior of the user by comparing the user's previous selection. This enables identifying the nearest neighbors. Yeah. So buyers with a similar decision history. All right. I think I already explained that. Now, also clustering is just a form of unsupervised learning where the labels or data points are unknown ahead of time. So it's the model that does that. Okay, I think these data points are similar, so these people are similar to each other. So when you come out, then the result is going to be a set of clusters, depending, but you're going to define the cluster, which is going to be the supervised part. So objects with the same cluster should be similar. Objects from different clusters should be dissimilar. The choices made beforehand regarding the number of clusters to be generated. So that's the supervised pass. So you're going to take, okay, from this data set, can I have 3 clusters? So the model is going to do, okay, based on the number of clusters you have stated beforehand, I'm able to categorize these people into this set of clusters. All right, and I'm talking about classification. So classification according to this human label training data sets. In this case, kind of supervised learning, where the categorization and classification of all feature inputs is ruled by these known labels. So for example, I can say, okay, people, so based on a particular data set, let's say score. So let's say the score I should write an exam and stuff like that. You already have a label form of score. Say, okay, if scores of this scores of the student is greater or equal to 70, isn't that person score A? So it's in the category of A. If it's between 60 and 70 and 69, then that person score B and stuff like that. So those ones are already labeled already. So whenever the model goes into the data goes into that kind of model, you just find label those inputs based on that that rules that is already laid down. So that kind of let's call it classification model. So this classifiers use the concept of supervised learning. So classification rules set by the training data, which has been labeled previously by the main expert, are applied against raw unprocessed data to find out their approach labeling. All right. So, so classification is often applied by email services, which tries to separate spam email before this land in our inbox. So it's just like if you should find some certain words, they will have put some certain words in the model, like okay, you should be able to find some certain words in this model, label it as spam and all of that. So that is classification for you. And talking about out workflows, the SaaS, out, SPSS, and most other statistical analysis applications include powerful tools for generating workflows. Most of these tools have intuitive GUI that make data visualization possible. My script also enable generation of statistical analysis workflow. So at the final data exploration and visualization stage, you can export to human readable format like JSON or CSV, or use tools such as Tableau desktop. We also seen this in the field that Mahat architecture sits on top of the Hadoop platform from this, yeah, from this place here. Sits on top of the Hadoop platform. So Hadoop onboarded the program by separating the tasks of program activity job. And in the same series, Mahat provides programmer-friendly abstractions of complex task code ready for implementation. So you don't have to stress yourself over writing some complex task code to build to do some model building and all of that because you already have the libraries already in Mahout. So that brings us to the end of this session. I will also encourage us to read and do some of our lab, the ones that are very, very important and very, very necessary, especially all your our labs. It's very essential for you to go through them. Hello, is there anybody still with me on the call? I think we are done with this the third module, which you should have passed this for a while now. So now we're going to move to big data analytics methods, which is the fourth module, and we are still going to like seven modules. Seven modules. So here we're going to talk about implementing a big data solution. Implementing a big data solution. This session is also it's not it's something you can be able to understand. At least go through it once. If you can go through it once, it's very okay. So you're going to understand, explain, you should be able to explain at the end of the session the steps to perform the envisioning process before implementing a big data solution. Follow a prioritization process for big data use cases. Explain the steps to perform the solution engineering process that can be used to implement big data solution. Also, at the end of the session, you have to explain some common challenges to implement a big data solution. I don't know, maybe we'll be able to cover this today, but let's see about like the next 10-15 minutes. So, so the evolutionary process defines how big data can power key business initiatives and where and how big data and advanced analytics can be deployed to transform a business. So big data organizations use big data to power their key business initiatives as follows. Google use big data, Amazon because Twitter, Facebook, they have a lot of LinkedIn. So they use big data solutions to promote their business and get useful business insights to make business decisions. So key business initiatives empowered by big data. So yeah, uncover new revenue opportunities, impact, marketing and sales. So big data gives you the power to uncover new revenue opportunities to impact, marketing and sales. So you'll be able to know, okay, where you should target this campaigns and all of that. Who are the target audience? So big data enables you to know that. Also research and reduce costs in various divisions of business, mitigate risk across all the operational and financial aspects of the organization's value chain, gather new customer, products, and operational insights. All right. So moving on to the next slide. So the engineering process helps the business and IT stakeholders understand the possibilities that open with respect to new big data sources and new big data technologies. Following figure shows an overview or gives an overview of the engineering process. So business and the IT stakeholders come together and okay, uh, to understand okay what are the values can you get from
big data sources like social media, internet, transactional data, or web docs, and all of that. And how can we, what tools, technologies can we use that can get us business value for the organization and all of that. So they come together. So the IT guys are the one that come up with technologies that's going to provide a reasonable value. Sometimes some big data technologies are easy to implement and gives uh, very impressive business value. But some so we're going to see a lot about that in when we talk about prioritization matrix. So here we said the following figure gives an overview of the revision process, talking about first of all do the research. So identify key business initiative objectives and time frame. So what are the our KPIs and key business initiative objectives, what are we trying to achieve, and what is the time frame. So what's the time gap we have? Okay, by this time to this time, because sometimes if it has to be timely, it has to be timely because if you don't get some results for a particular period, after that particular period, that result will be useful any longer. So it has to be timely. So analyze, prepare sample data, test out insights. So in this case, you have made your research, you've gathered some the necessary data, prepare and sample it. Also brainstorm. So envision potential of big data against big business initiative. Okay, okay. Will this data give us what we are looking for? In this case, that's what the brainstorming comes about. And prioritize opportunities, identify impediments. So in this case, you're going to see, okay, what are the opportunities I can find in this data better and all of that, and what are the values you can. So what are the limitations and challenges and all of that. So in this case, we actually this so put them in the prioritization matrix and see whether it's actually feasible to implement and all of that, and whether the business value is actually worth it at the end of the day. So documents which is the final stage, capture analytic opportunities and recommend next steps. So the big data emission process involves a number of steps that need to be executed. So going to the next slide now, this is the first thing talking about research and interview. So prior to the execution process, the business and IT teams need to identify the key problem scenario or the target business opportunity challenge and initiative. What are we trying to solve? So after establishing the target meeting, the participation team takes over. Uh, so this team typically consists of a lead facilitator, someone that knows about the subject matter, which is the subject matter expert also, and a data scientist or an analyst. So the team conducts interviews to take note of important points, initiatives, and issues. So in your material, when deep dive talking about this, you should also follow up with your material, very essential. Also, prepare data and conduct exercises. So, prepare data and develop client-specific analytics. After identifying the business initiative, participants to collaborate with the IT team to identify and acquire the relevant sample set of data. Because sometimes you have the internet data and you have the external data. So, the internet data, the ones that are actually reachable within the organization, then the external data, like the social media data, internet data. But that may be able to combine these two together. I think you get uh, a lot of insight from them. So the data scientists and analysts explore, enrich, and analyze this data using advanced analytics, data visualization techniques, and various statistical software. Also conduct envisioning exercises to understand what is possible. So class-specific stories using analytics with the data are created as illustrative examples to get the business and IT person to start thinking about, okay, having seen the analytics, the visualization, and all of that, you can really to see, okay, what is actually possible to do with this data we have as considering internal and both the internal and the external data, which is kind of the new sources of data. All right. Also brainstorm and prioritize.
So brainstorm and prioritize big data use cases. So the team brainstorms to leverage big data and operational data coupled with advanced and predictive analytics to power the targeted business initiative. So the team can review the client-specific evaluation exercise for visualizing publishing the new data sources and advanced analytic tools for making implementation use cases. So they also demonstrate a new business insight and monetization opportunities provided by application of advanced analytics. So you come up with use cases and okay, you prove out use cases. Yeah. You come up with use cases. Okay, then prioritize. Okay, which ones are so the ones you're going to consider are the ones that are easy to implement and gives the highest business value. So the ones that are very easy, that are the most easy to implement, and also at the same time gives the highest business value. So capture implementation risks. So capture implementation risks and business value drivers. So the final implementation step is to summarize, identify, and prioritize business opportunities and recommend steps for deploying advanced analytics in support of targeted business initiatives. So this includes key interview findings, so key interview findings as related to the business initiative, analytic use cases that came out of the efficient process, the prioritization matrix results, and recommended steps. I think I don't know whether they're going to show you the prioritization matrix in this slide, but let's move on. So prioritizing big data use cases. So prioritization matrix is a tool for driving business and IT collaboration and agreement around identifying the right initial use cases for the big data journey. So the use cases are based on the matrix based on 2 points. That is the business value and the feasibility of implementation. So you have a 2 by 2. You have a 2 by 2 matrix. Yeah, you have a 2 by 2 matrix. So it's either a high business value or low business value. So you can have your column, your y-axis to be the business value. So anyone below is going to be the one that generates a low business value. Anyone at the top is going to be the one that has the highest business value. Then the x-axis is going to be the one that has the feasibility of implementation. Now the one to the left part is going to be the one that has low feasibility implementation, and the one to the right of your x-axis is going to have the highest feasibility of implementation. So the one at the right most top of the prioritization matrix is the one you should consider. So prioritization matrix process. The prioritization matrix process starts by documenting each use case, identifying the brainstorming and aggregation stages. So business stakeholders are responsible for the relative positioning of each business case on the business value axis. So the stakeholder is the one that was going to say, okay, based on this thing that we have seen, I think this use case is going to give us a lot of business value. So that one to place that use case on the business value axis. Then the IT guys are the one that will say, okay, based on what we've seen that we can generate from this data, this is and this use case, this is the place this use case falls on the implementation feasibility axis. They are going to see how feasible is it to implement this use case. So the IT guys are the one in charge. So they are primarily responsible for the relative positioning of each business case on the implementation feasibility axis that wants. So that considers data, technology, skills, and organizational readiness. So let me see the next slide. So this is a prioritization matrix. So you can see it's a 2 by 2 matrix. So you have here this arrow here means high visibility. No, so high business value. Then anyone that falls around here is called low business value. Now this is implementation feasibility access. So any guy around here has so the business use case has low visibility. So it's very so the visibility is very low to implement that use case. Then this one here has a very high visibility. So anybody that falls around here, this rightmost top is one that has the highest the highest visibility of implementation and gives the highest business value. So you should consider that. So moving on to the next slide. I think I'm going to talk more about this prioritization matrix further more in the next slide. I'll be wrapping up very soon. We'll be able to finish today. So the following discussion can be made from the previous figure. So why is use case B more or less valuable than use case A? Which business drivers or variables make use case B or less valuable than use case A? These are discussions you are going to be talking about after you'll be able to put your use case and participation matrix. So it is critical to capture the reasons for the relative position of each use case in order to identify the critical business value drivers and potential implementation risk. So talking about the prioritization matrix traps, so you have four categories. Okay, so they are talking about three here, but it's actually four. This one, this two, this three, this four. So we're going to talk about three here. So prioritization matrix traps, just that you should avoid. To use the prioritization matrix, you need to understand the potential discussion traps. The use case that fall into the following matrix zone should be avoided. So these are the zones they are talking about. This, and this. This is the sweet spot. This spot at the right top is the sweetest spot because that's high visibility and high business value. So these are the traps that are talking about 1, 2, 3 here. All right. So the first one is that the zone of mismanaged expectation. So having each business value, these use cases are the least probable of executing this successfully and therefore must be avoided. That's why I call it zone of mismanaged expectation because it's very low. So it falls around this quadrant, the left bottom. It has low visibility implementation, but has a very high business value because it's not easy to implement, but it's seeing the picture, it's going to give you a very high business value, but very beautiful. So those kind of use case, they're going to it's going to take at the end of the day, it can just ruin you. You can just take the business down at the long run. So it's better to avoid this kind of use cases. Also, you have the zone of user disillusionment. And in this case, this one it has little business value. So with little business value, even these cases are easy to execute, but the business IT personnel should avoid them. So these are the ones that fall around this place, this part. It is easy to implement the use case, but it has a low business value. So that's what they call zone of user disillusionment because the IT guys are on something that as small as going on. So it's very easy to implement, but it doesn't give a good business value. You'll be able to run it, but then it's not giving much. And we have zone of career limiting zones. So say with least business value and low success probability, these use cases should be targeted by no person belonging to either business or IT. Sorry, I made a mistake. Zone of mismanaged expectation. Okay, I think I talked about that very well. That's one that fall around here. It has low visibility but has high business value. So that's why I said it's called a zone of mismanaged expectation. Though it has good business value, but it's very the probability of able to implement it is very low. It has a low visibility of implementation. But here, zone of career limiting moves is one that falls at the left bottom here. That it is not easy to implement and it does not have so Yeah, it's not easy to implement, so low implementation feasibility, and it also has low business value, so you shouldn't go there at all. That's why they call it one of career limiting goals with least business value and low success probability. So these cases should be targeted by no person belonging to either the business or IT, because first of all, it is not limiting, it is not very easy to implement, it's not easy to implement. It also has low business values, meaning that this idea is very hard to implement and it will not even give us profit. So what's the essence? So don't even go there, it's a no-go area. So so use cases falling into the above three zones are avoided because they either provide little business value to the business stakeholders or are too risky for the IT implementation. So uh, I would continue from here in our next class. So I'll continue from here in our next class. This is where we're going to stop because it's already past our time. So thank you for the. But before we call it a day, is there any question you want to ask at all before we call it a day?
For now, no question.
Okay. Okay. If there are no questions, I would say thanks for coming and we'll see you tomorrow by 2 o'clock. All right.
Thank you, Manuel.